at 3 p.m. on a Friday. I'm Alex Galiano, Gaia Grosso. We are both postdoctoral fellows within IAIFI. IAIFI is the NSF-funded Institute for AI and Fundamental Interactions. And on behalf of IAIFI, we want to welcome all of you to tonight's panel event. The context for this event is, of course, the 2024 Physics Nobel Prize, which was awarded to John J. Hopfield and Geoffrey Hinton, quote, for foundational discoveries and inventions that enable machine learning with artificial neural networks. This was the Physics Nobel Prize. This was somewhat controversial. Many people talked about this. Many people disagree with this being awarded the Physics Nobel Prize. Maybe we'll talk about that a little bit this afternoon. And so for context, we hosted an event, a fireside chat back in November, where we discussed this award. Thanks very much to the participants of that event. And to those interested in learning more about the event we ran back in November, you can see the full stream of it on our YouTube channel. But today, we wanted to dive more deeply than we did in November into the impact of Hopfield and Hinton's work, and more broadly explore physical insights, interdisciplinary research that specifically tackles the understanding of artificial and biological intelligence and the intersection between them. And we have the perfect people to be chatting about those topics with. So a little bit about the format of this event. We'll start off with general research introductions, kind of flash talks from the panelists. We have a set of prepared questions for the panelists, which we have been dying to ask. And we'll then open the floor to questions from the audience at the end. So we have a Slido link. The code is here. You just go to slido.com and enter this code. There's also a QR code on the screen, although this is going to go away when folks move to their slides. So at any point during this event, feel free to go to this link and upload a question. And at the very end, we will select some questions from you all in the audience. And we should mention, I've been told to say you're not allowed to eat in this room, but we have little Lindor truffles for anybody who asks a question. All right, so pull up your phone, feel free to scan that QR code. We want to get lots of great questions. Oh yeah, and of course, we're going to pass around the mic at the very end to bounce between the Slido questions and the questions that you all want to ask directly to the panelists. And also very important to mention is that immediately after this event, we will transition at about 4:30 into an IAIFI social, and you all are more than welcome to stay for that. We'll have snacks, we'll have drinks, and hopefully some of the panelists will be willing to stick around and chat a little bit in more detail with the more interested folks. Okay, I think that's everything I wanted to say. We'll get more details about the social at the end. With that, I think I will pass it off to Gaia.
All right. Hi, everyone. Yeah, but before diving into our conversation with the panelists, I want to say a couple of words to introduce all of them. So Dmitry, Ila, and Cengiz that are here, and please let's all thank them for being available today to share their thoughts about the research. I'm going to give like a few, let's say, words to introduce all of them. So starting from Dimitri. So Dmitry is a researcher staff at MIT-IBM Boston AI Lab, and it's also IBM research. Dmitry studies computational properties of neural networks, taking ideas from neuroscience, and he received his PhD in physics from Princeton University, and was previously a member of the Institute of Advanced Studies in Physics. Ila Fiete, she is a professor in the Brain and Cognitive Science Department at MIT. She's affiliated with McGovern Institute, and she's a director of the K. Lisa Young Integrative Computational Neuroscience, or ICON Center. Ila uses mathematical tools to study how the brain performs complex computations, and she earned the bachelor in mathematics and physics at the University of Michigan, and after that, a PhD in physics at Harvard University. Finally, Cengiz Pehlevan, he is a professor in applied mathematics at Harvard University and is also affiliated with the Kempner Institute in Harvard. The Cengiz group is working on attempting to develop algorithm theory for learning in the sensory domain, Cengiz received a PhD in physics as well from Brown University, and previously was a research scientist at the Flatiron Institute Center for Computational Biology. So with this, I leave the floor to them, and we'll start with this brief, let's say, summary talk or lightning talk from all of them, talking or introducing their research, and in particular trying to address the question how the work awarded the Nobel Prize impacted their own research, and giving an example in more details about something they're working on right now. And I think we start with Dmitry. It is all good for you. I'm going to follow with Ila and Cengiz.
Could I use the mic or?
There's a little switcher at the bottom.
Yeah.
Yep.
Right. Thank you very much for the invitation. Hopfield networks, they have played enormous role in ending AI winter that has lasted between 1974 and 1982. And essentially, they were the main reason why that period in the history of neural networks has ended. In its simplest form, Hopfield network of associative memory is an all-to-all connected Ising model. So you can think about it, the energy of this model in this form. So essentially, the dynamical degrees of freedom here are these classical spins, sigma I. And in this network, there are capital N of those spins. And the shape of the energy function is determined by this matrix Tij. In the typical setting, the most straightforward setting for this model, what is happening is the following. So you give me some data. This data is called memory vectors. And here in this cartoon example, there are 4 memory vectors, Xi1 through Xi4. And I'm going to do the following. I'm going to try to engineer this matrix Tij in the shape of this energy function in a way so that these vectors lie at the local minima of the energy. And then at inference time, I'm going to do the following. I'm going to start from some state. And typically that initial state is going to have fairly high energy. And then I will start flipping those classical spins one at a time. And I will only accept the flip if that flip decreases the energy. So if I keep doing it for a long time, eventually the system will reach one of the local minimum. And at that point, I'm going to say, I'm going to declare that the computation has stopped, and I'm going to read out the final state of this neural network. And hopefully when I do so, I should discover that the final state would correspond to one of the memorized patterns. So essentially, it's kind of like a memory system. You give me the patterns, I memorize them in the synaptic weights of this neural network, and then I retrieve that information from the synaptic weights of this neural network. So from this little description, you can perhaps see why theoretical physicists would love this idea, right? It's Ising model, it's spins, it's the stuff that we really love. And indeed, if you look throughout 80s and 90s, thousands of papers and dozens of books have been written studying various computational properties of this model. Specifically, back in the 80s, physicists and community in general were excited about the following question. How much information can we store in this simple system? And what they discovered is that it turns out that not that much. So it turns out that if you have a network of capital N spins, the best that you can do, if you're trying to store independent memory vectors, the best that you can do, you can store 0.14 different vectors. And if you try to store more than that, the network starts confusing them. And there's a whole bunch of reasons why this scaling relationship is extremely annoying and insufficient for practical AI applications. So in 2016, people revisited this question. And what they discovered that the source of that limitation was the sort of a little bit overly constrained formulation of the problem. It turns out that the reason why we have such a little memory storage capacity for this network lies in the fact that the energy function is quadratic in spins. So what instead of using a quadratic energy function, we would add higher order terms. So for example, imagine that we can take a product of n spins and then contract them with a symmetric tensor with n indices. That would also be a valid scalar energy function. And it turns out that if you repeat the same calculation that people have been doing in the 80s for this new class of networks, you will discover a much more favorable scaling relationship. So you can see that the capacity of the network now scales much faster than linearly as the size of the network gets bigger. Moreover, it turns out that you can even achieve an exponential storage capacity. You can store an exponentially large number of memories in this network as a function of the size of the network. So this idea has been called dense associative memory. And the reason why it's called dense associative memory is because the network essentially operates in the same amount of configuration space as the classical old Hopfield network from the 80s, but now the memories are packed in a much denser way inside this configuration space. And other things that people realized is that, first of all, dense associative memory is not just one specific model, it's a class of models. And that class of models can be split in various kinds of universality classes that are defined by the peculiar form of these scaling relationships. Another thing that people realized is that many of the standard tools in AI, mainstream AI architectures that people are using, they can be obtained as limited cases of dense associative memory. So, for example, attention operation, something that we commonly use in LLMs, is an limiting case of a certain class of dense associative memories. Transformers can also be viewed as limiting cases of dense associative memories. And the reason why this is important is that conventional AI architectures are a bit of a black box. It's very hard to understand the computation that they are doing. Now, if you map their computational properties onto dense associative memories, suddenly you can ask meaningful questions using physics toolbox. And that's why people got excited. So, moving forward. So if you look at the history, throughout, in the period of time 1982 through 2016, people were excited about small memory storage capacity Hopfield networks in the regime when the amount of training data is small. 2016 through 2023-ish, people got excited about large memory storage capacity, dense associative memories. But in typical applications, the amount of data that went into training these networks was still fairly small. So if we think about frontier and what's going to happen next, and this is my somewhat subjective opinion, but I want to share it with you anyway. I think the interesting question is what happens to large memory storage capacity in the regime when the models are big, when the capacity is large, but the amount of training data is even bigger than. And it turns out that in that regime, dense associative memories turned into diffusion models. Diffusion models, as many of you know, are responsible for producing these kinds of pretty looking images that do not exist in the real world, but you can generate them. And for this last slide, I picked this project that we recently completed, and please take a look at this reference that I put at the bottom of the slide if you want to learn more. But essentially what we have done here is the following. First of all, we took state-of-the-art diffusion models, and using the correspondence with dense associative memories, we mapped them onto the dense associative memories. Then, using the dense associative memory theory, we looked at what happens to the behavior of these models if you gradually train them on bigger and bigger data sets. When you talk about diffusion models, it turns out that if you take a diffusion model and train it on a small data set, it tends to memorize examples from the training set verbatim. If you take the limit of large data, diffusion models tend to generalize. But it turns out that that's not the end of the story. It turns out that there is a whole third phase that was entirely overlooked by the conventional computer science community. And that third stage, third phase that is shown here by the green curve, it's the so-called spurious states. So for those of you who know a little bit more about Hopfield networks than this high-level introduction, you know that spurious states is a hallmark of these models when they surpass the critical memory storage capacity. And it turns out that precisely the same spurious states appear among generated samples of state-of-the-art diffusion models. So the reason why I put this project on this slide, because on the one hand, it illustrates the utility of physics ideas and physics methods for understanding state-of-the-art methods in AI. And on the other hand, it kind of addresses some of the fundamental questions in Gen AI community. And the fundamental question is, how does creativity arises in these big AI models? And essentially what we are proposing here is that the onset of creativity, as the size of the data gets bigger and bigger, is facilitated by the emergence of these spurious states. And again, spurious states are the hallmark of Hopfield networks and dense associative memory when we cross the critical memory storage capacity. So yeah, I'm going to stop here.
We move quickly into Ila and we take questions after. So save your question for slide or later on.
Stop sharing. Oh, sorry. Yes. Great, thank you.
Okay, great, amazing. Well, it's nice to be here. Thanks everyone for showing up in the afternoon. So yeah, my work has been, profoundly influenced by the work from the Hinton, Boltzmann machines to Hopfield networks. And most recently, we published a paper, which I hope to tell you about, that tries to build models of memory, specifically memory seen in mammals. And it turns out the same memory systems in mammals that are involved in spatial memory are also involved in episodic memory, which is your memory of, autobiographical events, who you saw, where you saw them, what you talked about. Turns out there's a deep reason and deep connection mathematically for why these spatial memories are co-localized in the same circuit as episodic memories. And theoretically, some of the big reasons why tie into some of the theory that we have for Hopfield networks. So let's just jump in. So this is work that was done by Sarthak and Sue from my group. One big question for memory models in general, both from the theoretical physics side as well as from the neuroscience side, is this problem that Dima already alluded to, which was this problem of capacity. So if you look at a Hopfield network, these Hopfield networks are recurrent networks with symmetric connectivity. You can define an energy function in them, for their dynamics. But it turns out that if you have a network of order n neurons and n squared connections, so fully dense connectivity, the mutual information per pattern is of order n, right? Because their pattern is of length n, and these are binary states. And then you have of order n patterns that you can store in the system of order n bits per pattern. And then at that point, if you try to shove more patterns into the memory system, you get a catastrophic, well, worse than catastrophic, you get this thing that I call a memory cliff, where the system loses the memory of all past patterns that have been memorized, not just the ability to memorize new patterns. Okay, so this is this memory cliff over here. And then there are other versions of Hopfield networks that allow you to do some different things. You can sparsify the network, you can sparsify the weights, and so on. But all of them have like this sort of this theoretical bound on the memory that you can achieve with the order n squared weights, and that's order n squared, this frontier over here. And all of these different versions of the network touch the memory frontier, this bound, at one point, but then they have at different points. Okay, so the question is, are there any memory models we can construct that remain close to the memory bound for all different numbers of patterns that you store inside the network. Okay, so can you just remain at this order n squared information, storing, more information per pattern with fewer patterns and less information per pattern as you store more and more patterns without encountering this memory cliff? Okay, so that's kind of a question. So I just want to zoom out a bit, back up, and tell you about, the different memory models that are out there and that were actually part of this Nobel Prize that we're talking about. So there were Hopfield networks, which are fully recurrent networks where patterns are basically inputs that you give and induce an activity state on every node in the network. Okay, and they're fully recurrent. Boltzmann machines are a generalization of the Hopfield network in the sense that now you have two types of nodes. You've got nodes that are hidden nodes, and then you have the standard nodes that are like Hopfield network nodes. And so the hidden nodes, you don't directly drive the input pattern. So these are latent or hidden nodes. And so you kind of have these two types of nodes, and that's kind of the main difference there. Okay, so what's interesting, and the reason for having these latent nodes is that the latent nodes allow you to have effectively, like Dima talked about, like if you want higher order connectivity, one way to do that is to have, more than pairwise weights. You can have some higher order weights, but you can also achieve higher order effective couplings by having these hidden nodes, because a hidden node can couple many. One hidden node, if it couples n neurons, it's effectively an nth order coupling. Okay, so there's some advantages to having these latent nodes because effectively you have higher order couplings, but the problem is that learning is intractable in these networks. You have to have a huge number of samples to be able to do any kind of learning, and it's just basically they just don't scale. You can't do anything really with them. So the next innovation was to have to take this idea of these two types of nodes and separate them into a bipartite graph. So that now, instead of having all-to-all connectivity between all the nodes, now you have the hidden nodes up in one layer and the visible nodes in the other layer, and you only have connections from the visible to the hidden and vice versa. These models were much more easier to train. You just give an input and you can immediately compute the hidden state, and then you can iterate the weights and so on, right? So learning became very efficient. And in fact, historically, the reason why then these restricted Boltzmann machines became a big deal is because then Geoff Hinton wrote a paper showing, I think was it 2012, showing that you can take these Boltzmann machines and restricted Boltzmann machines, train a pair of them, and then do that for and then use the hidden layer as the input to the next restricted Boltzmann machine, stack them, and then you can do deep learning, where deep learning was previously very difficult to do. And it was sort of a shot in the arm for deep learning, gave people confidence that it could work. Of course, people don't use that strategy anymore, but that's what happened. Now, there was another physics Nobel Prize winner, Frank Wilczek, who some of you in the audience know. And it turns out that there's a paper by him, Baum, Moody, and Wilczek, which was a model for feed-forward associative content addressable associative memory. Okay, and it turns out that these feed-forward content addressable memories structured quite differently from all of these recurrent versions that came from Hopfield networks, but this feed-forward idea is something I want to return to because that's what our work does. So I want to argue that our work actually combines all of these elements to build a model that actually touches the frontier of memory capacity for all number of patterns stored in it. Okay, so what is this model? So just very, very briefly, I mean, there's a lot of detail here, but I won't give it to you. So basically, this is a network that has, it's a tripartite network. This is the high level states. These are actually recurrent modular states. So you've got, subnetworks that have some number of fixed points. These are nice pattern forming. These are called grid cells. These bidirectionally couple to a dimensionally expanded layer with random projections. So it's like fixed random projections into this high dimensional space, which we'll call the hippocampal layer. And then you have these learned projections back that are just learned once for self-consistency. So this whole bipartite network, which is grid cells and hippocampus, are basically a small low dimensional network that then projects randomly into high dimensional space, random down, self-consistently learned up, and then that network is fixed, call it the scaffold. And then there's heteroassociative learning between the scaffold states and the inputs, which is kind of like your feed forward memory model, like in the Wilczek-Baum-Moody paper. Okay, so that's kind of the idea, and this variations on this network can stabilize item memory, they're just like individual input memory. You can also use it as a spatial memory. So it turns out that these low-dimensional modular states actually each have a two-dimensional topology. So this is like actually a recurrent network that stabilizes the two-dimensional pattern and all shifted faces of that pattern. So you've got like a two-dimensional set of fixed points over here, and you've got another two-dimensional set of fixed points and another two-dimensional set of fixed points. And so if you have a two-dimensional velocity input, it can come in and it can systematically drive you around that set of fixed points, and that actually produces some nice properties. You can use the same circuit for episodic memory, where basically the previous state encoded in this dimensionally expanded hippocampal layer can then drive an effective velocity, which then moves you to the next state. Okay, so thereby you remember a sequence, and these transitions are low dimensional because these grid states are low dimensional. So all you have to do to recall the next item, the next state, instead of in a large network where the whole previous state, maybe an n-bit state, has to then contain the information to reconstruct the next n-bit state. Now instead, you construct just a 2D vector, just a velocity vector that just shifts these grid phases. And then that's all you need. You just need one 2D velocity vector to now reconstruct the next state via these hetero-associative weights. Okay, so we call this model vector hash. It turns out that, this model really, we can think of as this is a bipartite network over here, right? So we've got like the grid states, which are, fixed, and then they connect like an RBM to this hippocampal dimension expanding layer. We've got aspects of a Hopfield network because we've got these attractor states or fixed points over here. And then we've got this aspects of the Baum-Moody-Wilczek feed-forward mechanism, which is this heteroassociative association over here. Okay, so just this model, just to show you, it actually, here's the theoretical mutual information bound. And as you put in more and more patterns in this model, the memory recall stays close to that theoretical bound. And this is just showing you the mutual information that you can recover per synapse as a function of how much information you put in. And I've just shown you curves of various different Hopfield networks and sparse Hopfield networks and so on, compared to the performance of vector hash, which has near, asymptotically reaches a constant amount of information that can be recovered per synapse in the model, regardless of the number of patterns that you pack into the network. And so, it's actually, you can also beat, the performance, you can also ask, how does the performance of this model with these rigid elements and very simple learning rules, like Hebbian-like learning rules, associative rules, like in Hopfield networks, how does it compare to a memory network that's trained by just deep learning, where all the weights and all the activations are free? Okay, so it turns out that if we look at the recall performance of these kinds of very constrained models compared to a fully trainable deep network trained to do the same thing, the deep networks do much more poorly for comparable setups. Okay, so I'll just end here. So basically the idea is, what's different is that when you look at a Hopfield network, the basins of attraction, or the minima in the energy landscape that you can define for the dynamics of the circuit, are determined by the input patterns themselves. So the basins can be extremely different in height and in size. And in fact, people have not yet satisfactorily characterized the basins of the Hopfield networks. In fact, the more patterns you put in, the more the basins become very small. They're not convex either. In high dimensional space, they're super non-convex. There's some dimensions in which a single bit flip can move you at high number of patterns to the wrong basin. Whereas in this circuit, the difference here is that when you look at this grid hippocampal circuit, because of the nature of these grid states being very regular and structured in the form of these two-dimensional attractor networks, and many of them, it turns out that these grid states are extremely well spaced. They have all the same norm. And then random projections from the grid states to the hippocampus create a set of fixed points that are convex, we think provably convex, equal depth, equal width, equal radii. And then onto those minima, you can now attach external inputs just through heteroassociation. And this very well-behaved landscape, the nature of this landscape means that it's possible to recover from a lot of error. in the system. So I just will leave you with this image of a well-structured mnemonic clothesline. Okay, thanks.
We need to jump this for the last presentation, then more questions.
I just hope that slide will not come before me, but. Excellent. Okay, so I mean, yes, exactly, and my research has obviously been very much influenced by this pioneering work of this gentleman. And if you look at the, so I did get the Nobel Prize, obviously the citation, for foundational discoveries and inventions that enable machine learning artificial neural networks. And there's a much shorter version of this, like in the press release, they say, they trained artificial neural networks using physics. That was a pretty good quote. And inevitably, right, so this also triggered the idea of using physics to understand the trained neural networks, because at the end of the day, neural networks end up being complex systems, and it's not enough to just to train them, but also understand how they work. So this idea of, I mean, using physics tools to address this has been, very influential, and was also a re-emerging field, I'll say. And this is exactly what we do in my group at Harvard. We use tools from physics to understand how biological and artificial neural networks learn. So I'll just be very brief, try to make the connection exactly. Where does physics enter in this quest? So let's think of a feed-forward neural network. Right, so in goes some x, out comes f of x, and there's a bunch of parameters in between. I'll call them weights w, and let this theta be a concatenation of all of the parameters in this huge vector. So the main observation is that, training or learning itself is a dynamical system. And so basically, as you are updating these weights, there's some training time, and these weights go through some dynamics. And you can come up with different learning rules and optimization algorithms and so on and so forth. So let's study the simplest one, the gradient descent, right? So here is my version of it. The theta is the set of parameters. T refers to the training time. And this is the gradient term in the bit here over. So there's a training loss. Take a gradient of it and go along the negative direction of the gradient. And I just added a little bit of white noise just for the sake of it. But the point I'm trying to make is basically, just if you look at the gradient descent dynamics this way, you immediately make the connection, right? Loss is like the energy function for learning dynamics. And this is, again, an idea that Hopfield was brought in, that was very nice articulated by Ila and Dmitry here. In that case, the states of the network was going through a minimizing some energy function to arrive at an associated memory. This is another way to maybe be inspired by that idea and link to the learning itself, because you can also view updates of weights during training as minimizing energy function. And of course, conveniently wrote this way, because if you do it this way, you can study this dynamical systems using tools from physics. You could study the full dynamics, but just for simplicity for this illustration, I just want to note that the stationary state of this is basically a Boltzmann distribution. Right? So here the energy function being the loss itself, basically, and the a particular weight configuration being weighted by this exactly a Boltzmann distribution. Now, immediately, I guess in this audience, when you see this, all the tricks and tools that you learn in statistical mechanics classes or other physics classes come into play. So you can start analyzing these networks and their dynamics using all these tools. I've a bunch of things that appear in my own research, so large N limits, and could be the width of the network, depth of the network, number, some kind of parameter goes to infinity, saddle point approximation that arise from these kinds of limits, replica trick, that kind of stuff. So what can you answer with using these kinds of tools? Mainly, so I thought about this, maybe three types of questions. One is about expressivity capacity questions, by which I mean, this map x to f of x is a parameterized function, how rich is this function? What kinds of things it can express or not? You can certainly study these kinds of questions. Questions about generalization. I'm given a finite number of data to approximate a underlying function. How well does that generalize to the full data sets or even in and out of distribution? You can try answering these kinds of questions. And also some kind of interpretability kinds of ideas. You can try to understand the internal representations of these networks, or maybe the algorithms they learn to implement certain input-output relationships. You can try studying these kinds of problems. Just to give you an example that that these kinds of methods actually do say something about important problems in modern machine learning. Let's look at the example of this currently dominant AI paradigm that is of scaling. The idea that as you keep throwing more data and more parameters and more compute, the machine learning models become more and more powerful. Perhaps not a coincidence that one of the drivers of this kind of paradigm was a physicist, Jared Kaplan's paper, Scaling Laws for Neural Language Models. And being a physicist, he knew what a log plot was, so therefore he had the idea of plotting test laws on the y-axis as a function of, for example, number of parameters given a fixed data set size or number of data set tokens given a fixed model size. The computer is a bit more interesting. Also, it will take a bit more time for me to explain as I want. But the observation was basically, things get better as you increase any of these parameters. So therefore, maybe we should be building nuclear power plants to power our centers and GPUs, so therefore they can reach the AGI, which is still the dominant paradigm. But of course, you might be noticing that there's some power laws here that are not some exotic numbers, 0.095 and things like this. So you can try asking yourself where do these numbers come from, and then using the methods that I've described to you and the link between training dynamics and statistical physics, you can try coming up with theories. So I'll just highlight, I've been doing a bunch of papers on this area, but just highlight our latest version on this one. So this is plotting, for example, convolutional neural networks, test laws as a function of training time. These different curves correspond to different training, let's say, configurations. You don't have to deal with them. And the dashed lines is our theory. So I'm plotting two examples. In the left one, I get a good match. And on the right-hand one, I get a good match for certain regimes, but I don't get a match for another regime. So this is a question mark. This is still a research in progress. But I also want to highlight this because this also shows a physicist's mindset of approaching these problems. You try to come up with a theory, whether through approximation or simplification or something, and you test your theory, and when you don't get a match, you're happy because you have another problem to solve. And so, you might be surprised that it's not that common in machine learning domain. But if you apply this physicist's mindset, it's very natural to you. So I'll stop here just to conclude, basically. Another big influence of Hopfield and Hinton, and actually a generation of physicists from that era working on these problems was the idea that tools from theoretical physics can be helpful in understanding these kinds of problems. Thanks.
Thank you, Cengiz, and thank you everyone for the super exciting and inspiring presentation. And so we transition now to questions and answers, starting with some prepared questions. I'll start by asking, can you name one physical principle that has become central aspect of your research program and why, or more broadly, central aspect in your research community? And who wants to go first? There is no up to you.
To me, the the core principle is that physical systems compute, right? Harmonic oscillators compute eigenvalues of complicated matrices. Electric circuits can do the same. Neurons can do interesting computation too. That, to me, is the most important sort of lesson from Hopfield and from this whole era. But kind of, being more specific, in my personal research, the notion of energies, energy-based computation, that, you have a dynamical system, you have some kind of physical system that has a well-defined energy. And then essentially what happens during computation is that energy descends, right? And you can think about it in the following way, that essentially you can encode, when you design this energy landscape, you design that energy landscape based on the input data, based on the training data, and based on the task, based on the question that you want the neural network to solve. And then the energy descent happens, so the computation happens in the network. And then once it reaches the conclusion, it gives you an answer. And that kind of idea is very different, for example, from how feed-forward neural networks do computation. Because if you think about transformers, for example, transformers have certain number of layers. It's a feed-forward graph, right? So you give it an input, you pass it through a certain number of steps, and then it produces the answer. So if you ask it a simple question, it will give you an answer in 10 steps. If you ask it a complicated question, it would also give you some answer in 10 steps. There's no really mathematical capability for these feed-forward neural networks to, think a little bit longer if you ask them something a little bit more sophisticated. And the good news that Hopfield networks, dense associative memories, and all these kinds of models, they at least conceptually do have these capabilities. So essentially everything that pertains to energy landscapes, properties of basins of attraction, this is something that's near and dear to my heart, and that's the central principle that kind of, that kind of defines everything that I do, I would say.
Yeah. So for me, it's the idea that you can explain, phenomena at different scales with different effective theories. So if the goal is to think about a neural network, think about every neuron and try to come up with that kind of description. But that's not very useful. And then the point is are there more aggregate bulk quantities that somehow are descriptive and useful? So and these kinds of things arise naturally in physics theories, in some statistical mechanics theories, in the thermodynamic kind of sense, order parameters and quantities like this. I guess in this context, I'll call them summary statistics, a bunch of a reduced number of quantities that somehow close onto themselves dynamically that are useful. So this idea that trying to come up with an explanation in terms of these kinds of things is basically a basic. I'm not sure if you can call this a physics principle, but certainly a physics way of thinking, or basically a methodological approach to understanding neural systems. Yeah.
Yeah, to me, I think the thing that's closest to what physicists think about on a regular basis is emergence. The idea that, you can get something that, when you aggregate many small and simpler elements, you can get some very rich outcomes from it, is just a powerful way of thinking. And also, I think coupled with that is the idea that you get out more than you put in some cases, right? So, the current paradigm in deep learning, I would say, is not so much. I guess there's been these papers, very high profile papers, saying, emergence in deep networks, and it's very possible that now, we reach the scales and in network size and in data that you do see some genuinely, new emergent stuff, but also there's a big extent to which a lot of these networks, what you get out is, pretty much what you put in. You just put in massive amounts of things, and then you can sort of interpolate between them, and that's what the output is. But we know that, I think that's where physicists have a huge role to play. I think that we understand emergence, and I think there's a lot of room for emergence in these circuits that we can exploit to build much more efficient learners, much more robust learners. And those are just things that haven't really been exploited yet. So for example, in biology, there's all kinds of predispositions, genetic, genetic instruction towards a state that poises us. It's not like the genes are instructing every single synapse and every single weight and every feature of a neural network to give us intelligence. Rather, genes and evolution have put us to this point where we're poised to undergo, the brain undergoes pattern formation, over development, there's this sort of unfolding at a time, structure emerges, and that underpins learning very efficiently from very little data, right? In a way that's very distinct from current neural networks. And so emergence, I think, is the name of the game. And I find myself very influenced by those ideas.
Yeah, I'm so glad you mentioned emergence and kind of the difference between emergence of tasks and abilities that you can't solve, that you have not explicitly trained alone to do, versus the other, like you put something in and you get something out and you get out what you expected to get out.
Mhm.
As I've listened to each of your research overviews, it seems like the perception is that memory is very closely connected to how we think about intelligence. And I wanted to ask, is the goal of each of your research programs to achieve perfect performance on tasks that probe storage and retrieval or capacity and recall maybe? And if we get there, what will we still be missing in a computational model of intelligence? I mean, you were maybe chomping the bit with emergence, but yeah, what else are we missing?
Yeah, good one. You talked about moments.
Yeah, so my work, in my work, the question of memory is certainly very important, but and that's a little bit pertains to the last project that I brought up. I always find it fascinating that there is a huge community of people who care about memory, right? And that community typically cares about questions. You give me the data, I want to retrieve that data. So not much emergence. There's still a little bit of emergence there, but by and large, you essentially get what you give, right? And then there is a whole other community that cares about things of generating novelty, like diffusion models, LLMs. We want to produce stuff that is like really, really novel. Now, if you think about it, from the perspective of dense associative memories and Hopfield networks, I think you quickly realize that these are kind of questions, two sides of the same coin, for the following reason. Because essentially creativity and emergence is in some sense an artifact of misremembering. So you load the data, and then when you're trying to recall that data from the memory, you don't recall the exact data, but you make a mistake. And that mistake turns into creative thinking, right? And essentially, that is the kind of point of view that I think is getting increasingly appreciated by the Gen AI and associative memory communities, that these two classes of phenomena, emergence of novelty and creativity, and the ability to memorize things, they sound extremely different, but in reality, they're part of the same mathematical idea. It's just when memory fails, creativity begins, right? And in that sense, I would say that emergence and memory, these are not two entirely unrelated things.
Yeah, so great points. So when we talk about intelligence, obviously, not obviously, but we're talking about something that's not really well defined. First point. So there isn't really a consensus among people about what intelligence is, and then what its capabilities are, what its limitations are, what's the goal, and what defines an intelligent agent. So from that point of view, I mean, it's not really clear to give a good answer to exactly the question that you're asking. But we can say a few things, I think. I mean, and just a side point, given up until maybe a few years ago, the only meaningful example of an intelligent being was a natural being, right? So therefore, maybe we can talk about also examples of an artificial beings as well as intelligent. So ignoring the artificial aspect into aside, if you're going to talk about natural intelligence, well, there intelligence is serving a purpose, and that purpose is making the agent survive, right? Basically, or evolve, or I don't know, basically. So from that point of view, memory retrieval capacity maximization, I guess. I mean, it's not really the goal, right? The goal is basically to make the animals survive. And this aspect is helpful. If it is helpful, it's a good goal. That's what I'm trying to say at the end of the day. There are some neuroscientists where they were thinking about trying to formalize the problem in a way that maybe what you want to remember are things that are helpful in making predictions about the future. Because if not, they're not, maybe you just don't want to remember those things, or or they're useful if they're going to help you in a future situation to perform better, and I don't know, increase your chance of survival. So what I want to say is basically, to answer this question, it might make sense to think about first what intelligence means. And if we're going to talk about intelligence in the context of a natural being, this has to come into, you have to think about the goal of intelligence, right? From that point of view, yeah. It's not obvious to me that the goal is to actually maximize retrieval capacity, but I can say definitely that it's a useful feature to have in a memory system.
Well, that was a really good question, actually. So, I have to say that if intelligence equals memory, then I'm really not very smart at all. So I hope it's not purely the same as memory. But on the other hand, as Dima says, if it's about making mistakes, I'm brilliant, right? So yeah, okay, but I think that yeah, it's interesting. I think exactly like Cengiz said, it's really, memory is only useful insofar as you can use it in the right context, right? Given the current context, but you have to know what to retrieve so that it's actually of use, right? Of utility in the current moment, to act in the moment, given the current moment. And so I guess a large part of, the utility of memory is knowing what to retrieve and being able to access it quickly. So more than just the ability to store the memory is the retrieval aspect. And so, we've seen a lot of, back and forth in modern machine learning for example, in large language models, there's been this back and forth, the yo-yoing in the whole machine learning community for a long time about to use recurrence and temporal computation or not, because recurrent networks are just hard to train, right? So it was impossible to train them. So people wanted to get rid of recurrent networks. So then they came up with, let's give all the information in context in these transformer models, and then we can do away with recurrence and RNNs entirely, and that was successful. But then now as contexts grow big and the dependence on the context size becomes unwieldy because the things don't scale so well in terms of compute time with context length, then again, let's go back to let's add an RNN or let's add an external memory. So now we have these retrieval augmented memory models, which are now the main thing, right? But then the difficult thing, the difficult open problem is, how do you then use that memory, right? And how do you know what to access, when to access it efficiently, and then bring it to bear? So I do kind of agree that memory is a large part of intelligence. If you look at language models, that's mostly what they're doing, right? I think to the best of our knowledge, even now, they are still interpreting. As far as I know, any machine learning system that we know of right now does interpolation. And I haven't seen evidence that they do anything else. So to the extent that we think those are intelligent, memory might be all we need, right?
Yeah, that's perfectly sort of transition to our next question, because it's kind of really related with this. And it's about we wanted to pick your perspective about using human brain inspired AI for modeling, say, the next paradigm change towards AGI, or what's your take on this? Or do you think that this is going to drive AGI anytime soon?
30 seconds.
Yeah, maybe I should not answer the question. From my point of view, again, one way I define myself is a scientist studying intelligence. Until again, very recently, we had one kind of intelligence. So it's very natural that the way we think about it and formalize questions, and even engineer systems are basically motivated by by natural intelligence. Even in the cases like where you might think there is no motivation, there is some motivation, just the space within which you're thinking, the way you're addressing these questions are very much, natural motivators. I think what would be more interesting is actually if we ever get to another intelligent system that is not human-like. So that will be a very nice place where you can actually compare the studies and try to come up with basically like maybe more underlying principles, because we don't really know what we call natural intelligence is overfitting to biology's constraints, or there are like some more underlying principles that that could be generalized to different kinds of intelligence, and even though I don't know the example of intelligence. I'm going to inject one more idea here. I mean, we do live in a time that there do exist two kinds of intelligences. We can, let's say this, natural and artificial. And maybe it's a coincidence or maybe not that they're both driven by neural networks. Okay, and we can have an argument about whether, biological neural networks are the same as basic artificial neural networks or not. But it's a fact that, I mean, they do share some resemblances, one of them being idea of emergence, intelligence emerging through the collective behavior of smaller constituent units. And therefore, like I do see, maybe an underlying study, and maybe not very inspired with the approach intelligence, but an underlying sort of reason to study sort of emergent behavior in neural networks as a possible path to basic understanding intelligence. So from that point of view, obviously, if you take this point of view, you obviously don't want to turn your back to looking at the brain, because that's an example of an intelligent system where neural networks emergent behavior with intelligence. And therefore, I mean, either as an inspiration point or like just like, a way to test your theories, it's very valuable.
Yeah, so I wrote only one paper in my entire scientific life that really takes like a meaningful biological system and turns it into a meaningful AI system. And I'm going to spend like a few seconds to explain to you what this system is. That system is a fruit fly olfactory system. And essentially, what it does, it says like it's a two-layer system. It has a network of projection neurons that feed into the network of so-called canyon cells. And then there is like an interesting recurrent network motif that does a strong inhibition within the canyon cells. And essentially, whenever fruit flies smell, and rodents and like our olfactory system is not that different from that. So what happens is when the smell arrives, essentially because of this inhibitory motif, there is a barcode of how you code that smell in the layer of canyon cells. So a few years ago, my colleagues and I asked the following question: since this network is so well understood in biology, and we kind of know how it works experimentally, we know its computational function, can we use it for AI? And what we did is the following: we took that network, we called it in Python, and we feed in raw text into it instead of smells. And essentially, in the NLP tasks, if you're trying to understand the meaning of a certain word, for example, a word bank, that meaning can depend on the context. Bank can be a financial institution, it can also be a side of the river. And essentially what we try to do, we try to make that network associate the context of the word and the meaning of the word. And we train it on a bunch of raw text. And indeed, what is cool about that network is that it produced very meaningful word embeddings for real English words. And back then, these were state-of-the-art word embeddings if you are interested in binary word embeddings. Because, the cool thing about this network is that the barcode is essentially binary. Most of those canyon cells are in the off state, and you only have a few ones. And the location of those few ones encode the meaning of the word. And to me, that's like a meaningful way of using biological intelligence for building a powerful AI system. But the big problem with that logic is that if you look at the neuroscience, there's only a handful of systems that we really understand at that level of details. So, and usually those networks, they kind of exist in the early sensory pathways. It can be visual pathway or olfactory system. But if we move like to higher areas of the brain, there's a lot of like meaningful theories of the hippocampus, for example, right? But I wouldn't say that we understand them quite to that level of degree so that we could take their computational function and, bring them back into the AI system. And that's the main limitation that I see with this line of work, that, there's only a handful of systems that we really understand so well in biology. And, by and large, all those handful of systems have already been explored in the AI community in some sense. For example, if you think about convolutional neural networks, right? Historically, they have been inspired by Fukushima's neocognitron. And that network is pretty much the organization, the architecture of the visual system in human and in monkeys. And, there are such examples, but they're so limited that it's very hard to, scale it and kind of, do this, build it into a consistent research program. So for that reason, I admire biology, but I always try to get ideas from physics and then perhaps try to apply them to biology rather than taking ideas from biology and trying to move them into AI. And that's the main limitation, that we just don't understand brain sufficiently well to meaningfully use it.
I mean, time will tell. It's hard to say. The brain has a lot to teach, but whether neuroscientists are going to get there first in, sort of learning about the brain and then translating the insights to machine learning, or just a bunch of smart humans doing machine learning are going to sort of iterate and get there, faster. It's hard to know.
So we didn't talk a lot about this so far, but I wanted to ask, several of us work at the intersection of physics and AI, and lots of people are excited at the potential of using AI to drive scientific discoveries. And all of you have physics backgrounds and then work in AI. And I wanted to ask, to me, it seems like kind of the philosophy of physics is a reductive one. So you break apart a system, you try and uncover some fundamental physical laws, and then you see how general those physical laws are. Cengiz maybe alluded to this in the end of your talk, that right now it seems like AI is very much a question of scale and how much compute, how many parameters can we throw at a problem, and maybe everything will be solved if we just hope emergence happens, and then we'll come up with an enormous model that solves all of our problems. If we're most excited about using AI to drive physical discoveries, do we think it's going to happen at the reductive level, or do we think it's going to happen somewhere up the scale that we just haven't reached yet?
Yeah, great question. So first of all, I have to slightly disagree even with the premise of this question, because to me, physics is a little bit multidimensional, I would say. And reductionism is one axis, right? If we think about, I don't know, molecules, then we go to nuclear physics, atoms, nuclear physics, particle physics, then maybe string theory. Then yes, it's about making things easier and easier. But there's a whole bunch of other concepts. For example, emergence, right? So if we open some standard textbook on physics, say, Peskin and Sherman, quantum field theory textbook, indeed there is an axis of making things easier and easier there, right? But there are also many other themes, and to me, physics is cannot be reduced to that one dimension. So having said this, I do think that state-of-the-art AI models, they still do a little bit of reduction of complexity in the following sense. Think about it like this. Think about the physical system first. So let's say that we're studying turbulence, extremely complex phenomenon, right? But then most people believe that all aspects of turbulent flow can be captured by the Navier-Stokes equation. It's a very complicated equation. We don't really know how to solve it, but most people believe that if we could describe turbulence. And that's a form of reduction of complexity. Now think about neural networks. So let's say that we take some, relatively recent LLM like Llama, right? So Llama has like 7 billion parameters, like one of those Llamas. And, it's not like a terrible amount of weights that kind of, represent the computational capabilities of these models. You can store it on one GPU if you want, or maybe on a few others. Now compare it with the training corpus that those models have been trained. that training corpus is enormous. You need like a data center to store that training corpus. So if you indeed think about it in those terms, there is still a huge amount of reduction of complexity if you go from the data to the compressed representation that those LLMs have learned, right? And in that sense, I would argue that LLMs are a little bit like a Navier-Stokes equation. They still provide a compressed representation of reality. It's just the equation now has a little bit more parameters than what we are used to, but we're still doing more data compression in some sense.
I mean, that's a great point you made. So I do feel like, I mean, in a scientific, okay, so let me give this following example. You know, pre-Kepler in times, people observed, you know, planetary motion. And we can think of like Kepler's laws of the data compression, you know, instead of carrying books of, I don't know, planetary, I don't know, whatever, trajectories, we can carry with us 3 rules. But then, is that the kind of scientific understanding we want? Or for example, like, you know, Newton's law of gravity, giving a mechanistic sort of explanation of like what the planetary motion was. So I feel like, I mean, so this is, I don't think, by the way, this is more of a sociology question, I feel like. I think as scientists in many different domains, we are more used to sort of having mechanistic explanations as scientific theories. That's what we value. And there's a reason for this, because we believe, I think, if we understand the mechanisms, from there we can make better predictions and control and so on and so forth. Yeah, so it's any, yeah, so I agree with you that like machine learning models will learn trends, but yeah, I'm not sure like if they will learn the mechanistic underlying thing. So just to do a thought exercise, suppose we gave exactly this data set, like I don't know, planetary motion to and then make it make predictions. Will it learn, you know, Kepler's laws, or invent gravity out of it? And how would we know? But just coming back to the topic of complexity. So that the model is complex doesn't mean that, okay, so it's true that the model might be complex because it's a lot of parameters and so on and so forth. But, you know, at the end of the day, it might be learning with all these parameters, a simple input-output algorithm, and the questions can interpret that. And you would expect that if the model is behaving, generalizing well, out of what, especially if it's generalizing maybe out of distribution, you would expect that it has sort of understood the underlying principles or generating dynamics or something. So it has understood something about the world, right? And this is, you know, the main argument people give about, like why next token prediction in events will work, because to be able to predict the next token, you have to understand about how the world works. But I mean, it is possible that the models learn not the underlying principles, but I want to use the word statistical. I'm not sure if that's the right word, but some heuristics to make the prediction, which get it, but not exactly, but close enough to fool us. And then the question is like basically, does that constitute a scientific understanding? And then there's also the remaining question of even if the LLM is scientifically understood, how do they expect that principle from it? Yeah, that's also a totally different question. Yeah. I don't know.
Yeah, I actually, I'm just sympathical with everything that you said, Cengiz. And it's yeah, I mean, and I guess I took your original question to be one of how do we leverage these deep learning models to understand physics, right? And I think, right, you know, on the one hand, every model is just an approximation of reality, right? So in what sense does, you know, if a neural network is making accurate predictions, in what sense does it not count as an equally good phenomenological model, just with more parameters, as Dima says? Or on the other hand, you know, it's not satisfying, right? But maybe satisfaction is a vanity that we have where we want to be able to understand that model. And if we can't, then we say it's not a good model. So, but I mean, that's kind of one perspective. I guess I still think that there's a lot of value in compact models because in general, the compact models that we know generalize very well. And these very big models don't necessarily generalize very well. And so I think that, you know, but the problem, in my experience, the problem with these deep networks is that they don't like to find compact and sparse solutions. Even if the underlying data is compact, is sparse, and has like sparse factors and sparse clauses, they tend to utilize their whole high dimensional space in crafting the solution. So even when you put in regularizations, L1, L2 regularizations. So I think that some more, actually, there has to be some better conceptual improvements in how we think about training these models, or what rules we use to learn to drive the network to discover solutions that are very parsimonious and sparse, if possible.
So we transition to questions coming from the audience through Slido, but maybe before going through Slido, is there anyone that wants to ask a question in person here in the room? Please, yeah.
I'm a condensed matter physicist, so this is really a bit maybe condensed matter. Condensed matter physics, physics in general, we quite value locality of physical laws, and spin glass is precursor to the Hopfield network. So infinite being like an infinite rings sort of spin glass like model. We know the natural intelligence comes from physical laws which are inherently local. To what extent the non-locality of these networks actually give us some added advantage? Is there a sense it gives any added advantage? Then can one write down a local description which could have similar properties?
I can start. I think it's a good question. That's another form of regularization or constraint, right, in these models. And it's true that convnets are, have a locality constraint, right? Each layer looks at, a local region of the previous layer. So there is a locality, built into certain of these deep learning architectures, and clearly those convolutional biases towards locality have, really helped, right? So if you train a unconnected, unstructured, like a non-convnet, fully connected network on the same data, they won't do as well. So I think definitely there would be a role, right? So if you're building a model of some physical system and interactions, then locality is surely going to help. And so I think that in general, the name of the game is the more you can build in about your system, any prior knowledge that you have, and build that in, that's going to just help generate a more robust and more efficient solution in terms of how much data you need to train on.
Yeah, I agree with this view definitely, but it also points to, I think, a big open research problem following. Right, so I'm interpreting locality in local and physical space and local in time, perhaps. Right, so let's think of the following idea. So we learn well. We study things, we learn things, we're doing good. So that's all happening in our brains because synapses are increasing their strength or decreasing their strength. So think of a little synapse sitting in the middle of the brain. All it knows is basically, just the activity of the presynaptic neuron and postsynaptic neuron. So very little information, right? It has no idea about the rest of the brain, the state of the world, nothing else. It has to decide whether this, synaptic weight should increase or decrease. Right? So that's the constraint. It's interesting that you call this a regularizer. So I hope it's a regularizer.
Yeah.
I'm really hoping it's a regularizer. If it's a constraint, it's like a huge constraint in the information available to this, little synapse. Yet, brain as a whole collectively can organize and do meaningful things. And to be let's contrast this to how do we train artificial neural networks? And this is one of the main criticisms against backpropagation being not valid for Boltzmann. So one way to interpret backpropagation rule or gradient descent as basically bringing that synapse all the information it needs from the rest of the brain through this particular algorithm of carrying out errors to the earlier layers by multiplying this transpose of weights and so on and so forth. So, I mean, I do hope and believe and hope that this is a regularizer, but it also hasn't been possible, I think, that like people have been able to come up with neural networks that are trained with in a local way, with this local information, and get performant architectures to the level of, artificial systems. Just from an engineering point of view, if I hadn't told you that biology had these constraints, it would seem like not a good idea to make these asynaptic updates local because it's very, information inefficient, right? So I just don't know the answer, which way it is. I hope it's a regularizer. Yeah. Say something.
Yeah, I'm actually like, I agree with everything what both Ila and Cengiz said, but specifically I like this problem of making artificial neural networks train in a little bit more biologically realistic way. It's something that's kind of, the problem that is very near and dear to my heart, and I spend a lot of time trying to do that, precisely what Cengiz said. So essentially, kind of, like when you train a neural network with backprop, imagine that you have a network of, say, 5 layers, and you are trying to figure out what the weight between the first and the second layer should be. In order to do that, that neuron needs to have information about the state of all the other neurons in the whole neural network. If you train the networks in the standard way how AI people are doing this. In the brain, that's not the case. At least there's no biological evidence that something of that sort is happening. And at the same time, there is, I mean, right now it's not as popular, but 3-4 years ago, there was a huge amount of papers of different people, myself included, trying to build various forms of approximation of backpropagation algorithm that would match the performance of networks trained with backprop, with non-local derivatives. And I don't know if you would agree with that or not, but the answer by and large that it's very hard. So indeed, that non-locality that is extremely non-biological and extremely unsatisfying from computational principles, that is one of the main reasons why we need a nuclear power plant to train LLMs. Because if we didn't, if we had a good algorithm that allows us to do that, it would be much cheaper, like economically, and everyone would love that. But it's just a very hard problem, and it's never been shown that any algorithm of that sort can compete with backpropagation. But I think it's also a very interesting question, again, to second what Cengiz said. And I also think that in a funny way, these new networks that I've been talking about in my little presentation, that are recurrent neural networks, that have energies, right, that are not simple feed-forward neural networks, they have much higher chance of being successfully trained with these local algorithms than old-fashioned feed-forward neural networks that majority of those efforts went into like 3-4 years ago. So I honestly think that it's a very exciting question, and I think it's going to come back at some point. But at least at present, it does seem like these non-local learning rules, they're much more efficient than local ones.
Yeah, thank you. I mean, thanks for all this. Yeah, I don't agree with all these. There's a lot of work on this domain, but maybe what this is also pointing is that maybe we're not asking the right question. Okay, so maybe the question is to figure out, like, okay, so given the constraints of locality and given the and in neuroscience, experimentalists have actually done a lot of experiments about synaptic plasticity, and there's a plethora of different plasticity rules that people have come up with that depend on presynaptic activity, postsynaptic activity jointly, or maybe to other neuromodulators and all that kind of stuff. And maybe to ask, like, given sort of these constraints and these rules, what can be efficient to learn? So maybe it's true that like the brain has come up with locality plus these rules to solve certain problems efficiently, which may not be, I don't know, CPARTN or ImageNet or something, but obviously whatever it is that we're doing. So I think another way to approach this problem is change the question. I think, yeah.
I want to make sure we leave time for Slido. So I'm going to ask the top voted Slido question, which is there a physical interpretation of spurious states, and are there relations to creativity more phenomenological or based on physical insights?
It is 100% based on physical insights. It's a precise mathematical theory. And, whoever asked that question, it's quite a deep question, and I genuinely appreciate it. So essentially, if you take a diffusion model, the way diffusion models are trained, right? You take a data point and you add Gaussian noise to it, and you keep adding Gaussian noise for many, many steps. And after you do this, you would get essentially a probability which is a mixture of Gaussians. And that would be the likelihood of your sample, so to speak. So if you take the logarithm of that thing, that would be the energy, right? And that correspondence allows you to map diffusion language models onto dense associative memories. So it's not just some kind of phenomenological analogy or metaphor, it's a precise mathematical theory. And it's precise mathematical theory, and a lot of very smart people who worked on statistical physics for a very long time studied this phenomenon precisely in this class of models. And they have studied how spurious states emerge. And by the way, I didn't have time to give the definition of those states, but essentially spurious states are states that have distinct basins of attraction around them. But at the bottom of that basin of attraction, you do not find the training data point. You find something else. You find some kind of emergent thing that may be a mixture of a few data points, maybe something else. So that's what spurious state is. So it's a very well-developed and precise mathematics that goes into this intuition. It's not just phenomenological matter.
More general question, just about your career trajectories. So all of you were trained in physics, and I guess physics mindset in your training, and then you went into these fields, so machine learning and artificial intelligence and biological intelligence. They're mainly fields from computer science and biology and neuroscience defined there, and mostly still down there. In your research, do you find that you sometimes or often run up against a wall, like you feel like you cannot contribute in certain areas because you're training, you are kind of outsiders, so you have distinct perspectives, but you weren't kind of trained in the main domain of the topics that you work on?
Well, I can say a couple of things about that. So one is, in the beginning, in the early days of, say, DeepMind, right? They used to publish these Nature papers, and they had, some problem. They had a model. The model had a whole bunch of components, 20 components, and it was like, and then you would assume as a scientist, as a physicist, reading the paper, that all the components were essential components in the model. And it turns out that those were not essential components in the model. It turns out all of the components were included in the description of the model because there were a bunch of different teams that were all working on the problem. And then, the teams all made some pieces of things. And then, just to have them all, sort of contribute, they just have a model that has all the pieces without testing whether or not those pieces were necessary. So then now they do things like ablations and all of that, but it turns out in the early days of, the big papers coming out of DeepMind, just before even AlphaGo and stuff, that was the norm, right? It was the bizarre, completely foreign to the scientific mindset, how these works were done and how these papers and progress was reported. And that felt very, after I realized that, it was like, wow, okay, no wonder I couldn't understand why they have these components, because it made no sense. So that was one way in which I felt like a foreigner. The other thing is also that, there's a big sort of feedback dynamics in the field of deep learning, which is that, there's some initial momentum in some direction, and then stuff gets built, right? Like chips get built around, a particular route that is, the field has embarked on. And then now, because those chips are like the most efficient way to do training, people will only do algorithms that like exploit the abilities of those chips and so on. So we're kind of going down like a very specific valley in the space of potential different directions of research, right? And so in a sense, we're physicists, if we're trying to think about general principles of emergence and, intelligence and how, interesting behaviors arise, we can do that, but only in the context of this one very particular, we're only chasing one direction, right? So just being aware that there's a lot of potential non-optimality here, just because that's just the way the field has evolved.
Yeah, it's also very interesting. You're asking if I had hit a wall and trying to be a part of a different community. That's kind of the question, right?
Yes.
Yeah. So I mean, I must say, so my PhD has nothing to do with what I'm doing now or with a postdoc, even though the math looks similar. But I mean, my postdoc was basically, I feel like a second PhD. I mean, I did spend a lot of time. This was a theoretical neuroscience postdoc, and then I spent a lot of time trying to read literature, talk to people, and not just talk to physicists. It was very helpful for me that I actually worked with an experimental neuroscientist and hanged out in their lab and talked to these people and so on and so forth. So I made an extra effort, let me say, to be able to bridge this gap and and talk to people in those domains. So it is true that if you go to these other, I mean, neuroscience is a bit different than I think AI because it's a much more established field with its own traditions and so on and so forth. And so if you go to a different field and then I'm a physicist, I know better or something doesn't work. And so you have to fields have different traditions, questions. They value different kinds of answers. So you have to be all part of this. And once you start talking that language, you might be able to convince people that your perspectives coming from physics is also valuable. I mean, we are lucky because, there was already a generation of theoretical neuroscientists, physicists who's in this domain, and they've contributed a lot, so maybe people are more receptive. I think AI is a bit different at this time I joined. I mean, it was still young, and there were a lot of people coming from very different directions. There was already a tradition of physicists in neural network theory. I thought it was easier, but there was already like a language gap in terms of math, for example. Even like mathematical notation, the way you write an expectation value as a bracket will never work in machine learning columns will confuse people because they'll think it's a neural product. Even that kind of thing, right? So you have to, if I'm writing a physics paper versus a machine learning paper, my notation is totally different, for example, that kind of stuff. So you have to pay attention to those things. But if you can go over that barrier, I think there's a lot of things as a physicist you can take and convince people. It just needs a bit more effort.
Yeah, I should say that my experience is somewhat similar to what Cengiz described. And so certainly notations, it's just a disaster. So right now there is Einstein sum notation in PyTorch, and that's why computer scientists are somewhat receptive of writing tensors with indices. But a few years ago, whenever you put up something on archive and that something has some sort of implicit sums or indices in it, like people in the AI community, they just don't understand. And the problem is that sometimes and many times in the AI community, you have a tensor with many indices, and you cannot write it in vector because you need to contract along different dimensions, and along which dimension you contract matters. And somehow, in conventional notations, I cannot even imagine how you can specify it. You need to specify that in words. When you use Einstein notations or something like that, it's extremely elegant, right? That's why Einstein invented those notations. So this notation gap, indeed, it's a huge gap, and I completely sympathize to what Cengiz said. So the other gap that I found also somewhat culturally different between computer scientists and physicists is that physicists, at least the kind of physicists the culture that I come from, their motivation, their work is driven by ideas. And when you go to computer scientists, their motivation and their work is mostly driven by baselines, by data sets. And that's like a big cultural difference. And I don't know what the right approach is. So certainly data sets are important, right? Because if we build a beautiful mathematical model, but it doesn't do anything useful, it's a problem. But But somehow like that balance of convincing people that sometimes maybe it's worth investing a little bit more in a beautiful mathematical idea, hoping that down the road, if you put enough compute for this idea, if you back it with enough software engineering team, with a sufficiently big software engineering team, then maybe it will reach the performance of the data sets. That's something that to me as a physicist is a very natural thing to do. Like think about big projects like Manhattan Project or something of that sort, right? Or CERN. So, you know, idea comes first, engineering comes next. In computer science community, that's often not the case. Often the research questions are rotating around what kind of APIs a certain PyTorch package has. And, you know, if you cannot modify that attention mechanism, that flash attention would going back into the CUDA code, then nobody pursues that question, despite the fact that that could be a very meaningful modification. So that is also like a big sort of cultural gap between the kind of community that I'm coming from and the more mainstream computer science community.
Thank you for all your valuable contributions. We close with one last question, more like kind of punch from your side. What do you think is going to be the next big scientific breakthrough that involves the use of AI? Or in other words, what do you think the next Nobel Prize involving AI is going to be?
Fusion.
Yeah, I mean, hard question indeed. And I should say that I don't work on applications. So my sort of, you know, domain of interest, how physics ideas can improve AI, right? But if you kind of like look at the main trends that are happening in, you know, out there, I would say like there is a huge interest in long context model. Like things like, you know, you take an LLM and you try to run it not on like thousands of tokens, but on millions of tokens. And perhaps even hundreds of millions of tokens. And, you know, by and large, like these kinds of applications, they are not particularly useful for NLP tasks because it's like most of the questions in NLP, they do not require long context. You know, like those data sets that the reason why people work on long context, because they design very artificial data sets when they take some kind of, you know, fact that is required for answering a question, and then they hide it within millions of destructors, and then they're trying to extract that fact. But it's somewhat unnatural setting, and you know when we talk about natural language, that's not really what you know we mostly care about. On the other hand, if you look at computational biology, that's an entirely different story because genomes are long, right? Like human genome is 3.2 billion base pairs. And it seems quite natural that you know these kinds of research that is now actively being pursued in the NLP community might impact computational biology, genomics, like those kinds of sciences. And indeed, there was a Nobel Prize that is somewhat related to this for the protein structure, but protein structure is a very how should I put it? It's a very I don't want to say old-fashioned, but it's a very well-defined problem. People knew about this problem like, you know, 10 years ago, 20 years ago. It has been an internal problem that the field could not solve. But there's all kinds of problems in biology and genomics that are less intuitive, right? You give it a genome and you want to predict whether or not the person will have a cancer and what kind of cancer and how we're going to treat it. So I think all the technology that is now being developed in the LLM community might at some point impact computational biology in that aspect. But again, I'm an outsider, and I would be a terrible person to make such a prediction.
I'll just say I'm excited about what might be happening in robotics, and I don't know what will happen, but I think it will be tremendously interesting to see what's going to happen in brain-computer interfaces, because that would be an area where like we'll have to really understand how the brain works to be able to interface with the AI. So that's awesome.
I don't have too much to add. I mean, I'm just saying that, you know, energy is a big problem, and you know, to the extent that machine learning can help, you know, guide human reaction experiments, that could be a huge breakthrough.
Give a huge round of applause to all of our Just spend the last hour and a half with us. We're gonna take a couple minutes break and then we're gonna have a reception just outside to the left. So maybe around 4:45, we'll have snacks and drinks. Oh, it's already set up. Great. So yeah, feel free to grab snacks and enjoy your weekend. Thank you.